Yesterday, we calculated some areas. Specifically, I was carving up this rectangle, this 3 by 9 rectangle, uh, with some parabolas. And we kept calculating that the smaller area was 9 and the larger area was 18. Finding the smaller area is 9 or the larger area is 18 was definitely not the point of the problem. A lot of times we think of definite integral as being able to find the area under a curve and above an interval. But really, it's more than that. We want to take it a step further. We want to do more analytic geometry. So the analytic geometry aspects of this problem are messing with parabolas. I think that's the technical term that we use for this. Messing with parabolas, number one. And number two, setting up definite integrals. So this was a problem. These problems were about setting up definite integrals. So we want to be able to set up, when we're calculating an area, we want to be able to set up multiple definite integrals because sometimes one will be more convenient than the other. In the case that we had yesterday, and in this area here, A1 and A2, even though x squared is not invertible in general, it is invertible on this interval. For the picture that we have here, x, our function, is invertible. So I can describe y equals x squared. I can also turn this around and describe it as x equals the square root of y. So I can write this as a function of x or a function of y. Then it's just a matter of deciding which delta variable we want to use. So the important setups here is to know that we can calculate. Let's suppose we wanted to set up a definite integral for the area A1. There are a few options. I could do the standard delta x. Because this is a function of x, we can write this as a function of x. It's most convenient to write this as a function of x. So that's the thing that makes the most sense. So here's going to be a delta x. And here's going to be my x. Then what I need is the height of this rectangle. And the height exactly corresponds with the y coordinate at that point. So for that delta x, if I want the area of that rectangle, I'm going to use y times delta x. I'm thinking the area of this rectangle. The height is y, or the length is y, and the width is delta x. But we can't integrate y dx, not in single variable calculus anyway. So we trade our y for a function of x. So I have to use the fact that y is equal to x squared and replace my y with x squared. And so this is the area of the rectangle. Then we add up all such rectangles. And then we do an infinite number of rectangles. And then we get the total area, A1, is the integral of x squared in the continuous sum, the delta x becomes dx. And then we evaluate over all the values of x that are in play. And the x's go from 0 to 3. and then we get the 9. This would be the standard way. This is like one of the early examples of finding area under a curve. But this is not the only way we look at this problem. We could also think about the area with a delta y. We want to be able to think about this in terms of with a delta y as well. Not because we want to find the area, but because we want to make our analytic geometry skills more flexible. So here is a delta y version. So now I'm reading the area of this rectangle. Now I've got the length here does not notice that down here, this length does not correspond to x. X is from the origin to this point. I want from this x up to 3. So the area or the width that we're going to choose here is 3 minus x. Times delta y. I don't just put x in there because that's not what we're looking for. X starts at the origin and ends at the value x. I want from the value of x up to 3. So I want that difference. So I'm going to take 3 minus the x. And once again, we have a problem because this is a function of x and we want to integrate dy. So now I'm going to have to replace x with square root of y. So I'm going to rewrite my length as 3 minus the square root of y delta y. So instead of watching my x squared values grow from 0 up to 9, x starts off here as 0, and then the heights increase up to 9. My height is now going to start off when y is equal to 0 at 3 and shrink down to 0. So a1 will be the integral of 3 minus y squared, or sorry, 3 minus square root of y. In the continuous sum, delta y becomes dy. And now we integrate over the values of y that are in play. Y starts off at 0 and goes up to 9. We can integrate this by hand because it's a nice simple polynomial. I'm going to go over here on my calculator. And I'm going to type it in on my calculator. I have an invisible calculator, so. And it still works out to be 9. Here, let me grab my calculator and show you. See, 9. I mean, you have to round it off. I mean, but there it is, round it off. It's still 9. So the game that we want to play is drawing these slices. We want to imagine we can imagine this area as a bunch of rectangles. We can think of it as a bunch of rectangles that are books lined up in a bookshelf going in the x direction. That's a delta x slicing scheme. Or I could stack the books vertically because I just want them to look nice on the shelf and I'm not going to have to pull out the books in the middle all that often. So I'm going to stack them vertically with the delta y type of slicing. Any questions? The point is we want to read what's going on and try to be flexible in our analytic geometry and not just try to follow one procedure all the time. We don't just want to follow one procedure and try to follow a formula. Make sense? We can do the same thing for this A2. If we're going to calculate the area A2, there's a few rectangles that we can use. I could slice, I'm going to imagine A2 as a bunch of rectangles. And I can either have books on a bookshelf, they have magnets, so that's why the bookshelf is up above. And so I put magnets, and so they like click up instead of down on the shelf. So I could use a delta X. Here's what a delta X in that in the region A2 will look like. So this is still using a delta X. And we're still trying to imagine what the area of that rectangle is. In this case, the part of the rectangle, the height of the rectangle, or the length of the rectangle, is going to be not a y value, because y is from the x-axis up to the function. I want to go from the function up to 9. So for my area of the rectangle, I'm going to have 9 minus y. That we're going to have to convert because this is written with a delta x, and I want a function of x. So I just replace my y with x squared, because that's the relationship between x and y squared. So this is going to be 9 minus x squared times the delta x. So A2, that's the region where that little rectangle sits, is going to be the integral of 9 minus x squared the delta x becomes dx in the continuous sum. And then I integrate over all the values of x that are in play, and the x's go from 0 to 3. What we're doing is taking the expression 9 minus x squared dx and evaluating it at all the x values from 0 to 3, then adding up the results. And then hopefully this works out to the 18 that we expected. Some things to note here is that when I wrote area of rectangle, I wrote in parentheses 9 minus x squared and then the delta x on the outside. If I don't have those parentheses, then only the x squared is multiplied by the delta x, and our expression doesn't really make any sense. So I need parentheses around that 9 minus x squared. So I want that difference to be multiplied by delta x. So I need grouping symbols to say multiply the difference by the delta x. When I started writing the integral, I left off the parentheses around 9 minus x squared, because this dx doesn't really make sense without the integral at the beginning. So I was being a little bit lazy, and I was just taking the dx and the integral sign and using those as grouping symbols. It's a little bit lazy, but fairly common. This is why on quizzes that you turn into me, I might call, oh, you left off your parentheses if you don't have them here. But then all of a sudden I didn't care when you were writing the definite integral. Any questions? Yeah. We got to be careful with our grouping symbols. This is not the only way that we could have split up this region. We could have stacked these books not vertically, but or horizontally, but we could have made a vertical stack of books. So that would be using, with the same x and y being labeled, I could slice this way and stack my books. So this is still using a delta y. The area of the rectangle is still length times width. So in this case, my height is going to be delta y, and my width is going to be exactly equal to x. So I don't have to do any extra work. I can just say the width is x, because I want the distance from the y-axis out to the function. That's a horizontal distance from the origin. That's x. And then my delta variable here is delta y. Now I can't integrate x dy, so I need to trade my x for a function of y, and I'll use the same thing that I used before. X is equal to the square root of y, and then, oops, square root of 9, square root of y. Square root of y. And now my function and my delta variable agree. So now when I calculate a2, I can take the integral of the square root of y. Our discrete delta y becomes the continuous dy. And I can integrate over all the values of y that are in play from 0 to 9. Either calculate this by hand because we want some practice, or grab a calculator. Questions? What we're thinking about here is we're thinking about two different things. What's x between and what's y between? That's the thinking that goes into setting up these definite intervals. What's x between and what's y between? That's what we're trying to think about. What's x between and what's y between? When our shape is just a rectangle, x is between 0 and 3, and y is between 0 and 9, and it's always the same, then we just get to say 3 times 9, 27. If x is always between 0 and 3 and y is always between 0 and 9, then pretty simple. Here, the integral is giving us a fixed values of x. So there's where we're doing a fixed, what's y between? Y is between 0 and 9. So for all the y's between 0 and 9, what's x between? So the thinking down here, when I have this integral from 0 to 9, I'm saying y is between 0 and 9. For a particular value of y between 0 and 9, what's x between? So it is what's x between, what's y between. So the integral says that integral says y is between 0 and 9. The function that we're integrating is where we say what's x between. For each of the y between 0 and 9, we're saying x is between 0 and the square root of y, 0 and the function. It looks like we just wrote square root of y. That's because we don't write square root of y minus 0, the thing at the end minus the thing at the beginning. If we carry out that same kind of thinking, what's x between and what's y between on a1 with the dy integral, this integral is still saying the same thing. This is saying that y is between 0 and 9. And then the function that we're integrating is telling us that for each y between 0 and 9, x is between the square root of y and 3. Starts at the square root of y, ends at 3. That distance is just 3 minus the square root of y. This is the thinking that's going into setting up these definite integrals. Think about what's x between, what's y between. It's important to have this kind of thinking in play, not because it's going to be important in answering some questions on the upcoming final in Calc 1. It's not even going to be relevant when it comes down to answering questions in Calc 2. In Calc 2, you have a lot more things that you have to deal with than just finding area. They're all variations on the same thing. But if I have a function, let's say of 2 variables, then I might have to start asking more questions, not just what's x between and what's y between, but what's x between, what's y between, what's z between. That's all we're trying to describe here with these integrals. And being able to think about each of these regions in 2 different ways, a delta x and a delta y, is useful. Questions? Hard to determine if like describing these areas with like what's x between and what's y between and setting it up this way lands the way I want it to land. But this is kind of a forward thinking talk about finding area. And I don't get to find out until Calc 3. Oh, that's the great dilemma of math classes. You want to prepare students for things that they're going to encounter in the future while still making relevant to the things that they're working on. But then the students are like, why do I need to know this? I'm not going to need to know it for another year. I'll figure it out then. And then a year later, they're like, why didn't they ever teach me this? At one point, I had a group of students in 1 year, and then the schedules switched up, and I had the same group of students the following year. So I had them in like the pre-calculus class for a whole year, and then I became the calculus teacher. So I had them in my calculus class, and I was going over some review stuff. One of my students was like, didn't we learn this last year? I'm like, I don't know. I taught it last year. Let's find out if we learned it. Any questions? How's that, Reverend? Everyone looks so sad. We're almost done. Yeah, I don't want to force you to be happy. If you want to be miserable, that's cool. So this is just highlighting the thinking about how this works. The other thing that was going on was messing around with our parabolas. We noticed that if I just kept cutting through this rectangle, whether it's oriented up and down like this or side to side, I just kept cutting through this rectangle with a parabola. So when the horizontal was 3 and the vertical was 9, then we have 4 different parabolas that we can describe. So I had a 3 down here. Now, there are a bunch of different places I could put a parabola. Down here at this point, if this is the origin down here, if I have the vertex down here, then I was describing this as y equals x squared or x equals square root of y. The one that we had yesterday, I don't actually remember, but we had one where I put the vertex up here and dropped the parabola down this way. The parabola that has a vertex up here, this is where we said y is equal to 9 minus x squared. The function 9 minus x squared is not invertible in general, but it is invertible on this interval where x just goes from 0 to 3. When x just goes from 0 to 3. So I could just invert this and by solving for x. So if y equals 9 minus x squared, then x squared, then x squared is equal to 9 minus y. And then we just square roots. And in this case, I want the positive square roots. So if I want above that downward facing parabola, I would say 9 minus the square root of 9 minus the square roots, sorry, 9 minus 9 minus x squared, which is just going to be x squared. If I wanted to the left of this downward facing parabola, that would just be 9 minus the x coordinate here is square root of 9 minus y minus 0. If I wanted to the right, it starts at the square root of 9 minus y and ends at 3. So I would call this distance in here 3 minus the square root of 9 minus y. What's y between? What's x between? Yeah, here with my x-axis. So here's where I put the vertex on the y-axis. There are other places that we could put the vertex. I could have put the vertex down here in this corner. There, the vertex is at 3, 0. Now we're gonna have to deal with do some parabola stuff. But if we put our vertex at 3, 0, I'm just taking the parabola y equals x squared and shifting it over 3 units. And I only drew half of it because I only need half of it to slice this rectangle up. Now notice that if I try to turn this around, if we write y equals square x plus, if we write y equals the square of x minus 3 and try to solve for x, we're going to introduce some plus or minus. The same thing did happen over here. We just kind of glossed over it. Because we said, well, we're over here. We want the positive values of the square root. So if we go over here and solve this, y equals x minus 3 squared, the first thing that happens is we do the square roots. And so that means plus or minus the square root of y is equal to x minus 3. And so we get this, x equals 3 plus or minus the square root of y. We want to read this as 3 is that middle x value, and then we plus or minus the square root of y. That's what builds the parabola. Here's 3 in the middle, and I want the side. If I want to describe this branch of the parabola, this is on the left side of 3. That means I must be subtracting the square root of y. So this side I would describe as x equals 3 minus the square root of y. 3 plus the square root of y would be the side of the parabola on the other side of 3, on the positive side of 3. I want the part of the parabola that's on the negative side of 3. So this left side is 3 minus the square root of y, because 3 is in the middle. The right side, that's 3 plus. The 3 is in the middle. And there's one more. Here's our vertex. Let's suppose our vertex was at 3, 9. So I'm going to draw a flat here. So we've done a few things here. I've moved the vertex. I've taken that x squared and I've shifted it over to 3. So the x coordinate of the vertex is going to be at 3. Then I've moved the whole thing up 9 units, and I flipped it around that line. Or better yet, I shifted it over 3. That shifts it over 3. Then I flipped it to face downward. And then we moved the vertex up to 9. A similar thing is going to happen when we flip this around for the x coordinates. To turn this around for x coordinates, if I write y is equal to 9 minus x minus 3 squared, if I want to solve for x, x minus 3 squared is 9 minus y. Here's where we'll do the square root thing. This is going to introduce a plus or minus. We're going to have to make some decisions. And then we add 3. And so we still see that 3 in the middle. And that plus or minus square root of 9 minus y, one of them is the left side. The negative square root is the left side. The positive square root is the right side. So if we happen to be using this parabola to split this rectangle, I would say x is 3, and this is on the left side, because 3 is in the middle, and I want stuff that's less than 3. So I'll subtract the square root of 9 minus y. Any questions? That's just putting a vertex at one of these four corners. 0, 0. Here's the vertex at 0, 9. Here's the vertex at 3, 9. Here's a vertex at 3, 0. How's everybody, right? We're trying in this problem to increase our analytic geometry skills. It's not about finding the area. It's better to know more ways to do a thing than it is to know one way to do a thing. And it does not matter how fast that way is. Speed is never the issue. It's never about how fast you can do a problem, or at least it shouldn't be about how fast you can do a problem. It's about how well you understand the problem. I realize that you and I have different goals in this regard. For me, the important thing is how well you understand the problem and the process. For y'all, it's about how to score points. And that's like the one thing that you're concerned with. How do I score points so I can go and take the next class? How do I get out of that class so I can take the next one? How do I check all the boxes so I can get my degree, which is my automatic pass to making a lot of money? Spoiler alert, it's not, but we want to be flexible in how we understand things. We do a lot of work with let's actually just let's just do this. Let's take this parabola. I'm going to build another parabola. I'm all about parabolas today. This is going to be the middle. They're so much harder to draw when they're big. So here we got this sideways facing parabola. If we slice this function up vertically, I have two different functions, the top of the parabola and the bottom of the parabola. So vertically, this is inconvenient for us. There's a top parabola and a bottom parabola. It doesn't mean it's impossible, it's just messier. So vertically, Vertically, we have to be dealing with two functions of x. The top half of the parabola and the bottom half of the parabola. Horizontally, we only have one function of y. In this case, an integral involving a delta y would be more convenient than an integral involving delta x. For a particular value of x, there's two different values of y. But for each value of y, there's only one value of x. We can see that if we write down what this parabola is. This parabola is more easily written down as x equals y squared, with a vertex at 3, flipped over, now if you're thinking, dude, are you being a little bit lazy using the same 3, 9 vertex that you used in the last problem? 100%. It's Friday. How hard do you think I want to work? If you were thinking, not very, you are correct. If we solve for y here, we're going to have that top and bottom part, that plus or minus that shows up. So solving this for y is the same thing. We'll have y minus 3 squared is equal to 9 minus x, and then square rooting is where we get the top and the bottom parts of the parabola, and then we move the middle. We want to think about when we're dealing with parabolas, we really care about where that vertex is, and that vertex is at 3, 9. In this case, vertically, we've got 3 in the middle, and we plus the square root and minus the square root. Plus is the part above y equals 3, minus is the part below y equals 3. The reason that I go into so much detail is that for the most part, you're told to use the quadratic formula to solve your quadratic equations. And so you lose sight of all the cool stuff about parabolas for the sake of programmable expediency. You grab your calculator and you can have your calculator solve your quadratic equations. Oh, I have the Dwayne "The Rock" Johnson edition of the quadratic function. I forgot that I put that in there. I may have been goofing off in trigonometry a little bit. Had I done that? Oh, well, there it is. We use the quadratic formula. The quadratic formula is trash. We lose this like negative b over 2a plus or minus then the stuff. We want to figure out where the middle is, and then we can figure out how far from the middle on either side. We want to exploit the symmetry. Here's the middle, and here's the symmetry. It's plus or minus the same expression. There's the symmetry. All right, so it was about analytic geometry the whole time, which is half the title of this class, so you should not be surprised by that. That's going to do it for today. That's going to do it for this week. Some final exam problems have appeared on the canvas, and also, well, in a Word document that I'm going to hand you during the final exam problem, the class portion. So there are some final exam problems for the at-home portion. You can get started on those. I'm not sure when I'm going to be grading them. Probably next week on Tuesday, I'll go through a round of grading. So if you want to make corrections, you'll be able to make corrections. There will be others. That's it for today. That's it for this week. I'll see you all on Monday. Everybody have a good day. Have a good weekend, and thanks for playing.